Good afternoon and welcome to today's webinar titled EMS for Inventor, where we will understand how to model and simulate inductors using Autodesk Inventor and EMS for Inventor. My name is Arvind Krishnan and I work at the Product Management Department here at Emworks. The agenda for today is we will start with a very quick introduction to our company Emworks. We'll take a look at its products and the applications where it fit in. Then we will jump into the topic for today, which is the inductors. We'll learn a little bit about inductors, how they are classified and so on. Next we will learn how inductors are simulated inside EMS. And then I will show you a live demonstration of EMS for Inventor, where we will do a pretty detailed example of an inductor inside Autodesk Inventor, and finally we will open the floor to for any Q&A regarding this topic. Okay. Again, on behalf of Emworks, I welcome you all for today's webinar, and I just want to let you know that the recording, today's webinar is being recorded, and this recording will be posted on the internet, and you would be sent a link to this recording that you may share with your colleagues and friends. And as a part of today's webinar, due to the Q&A session, we encourage all the participants to type in your questions in the console window of the GoToMeeting where it says chat. There you can type in your questions as a message, and then at the end of the webinar I will actually be able to answer them in the order that they were typed in. Okay, so we can commence. Let me start with EMS, Emworks and the product EMS for Inventor. EMS for Inventor basically comprises two major categories. It is EMS electric that deals with electrostatic, electric conduction, AC electric type of problems where we have charges and voltages but no current or no coils. Then the next classification is the magnetic classification, which is EMS magnetic. That consists of three different study types: magnetostatic, AC magnetic, and transient magnetic, where we have coils and currents and excitation and the magnetic field due to these things. That's when you will use the magnetic module. In addition to it, we have add-in modules to EMS for Inventor. Coupling to thermal simulation is one where you can study the temperature distribution due to heat that is generated due to currents. It could be eddy currents or it could be currents in the winding. You can also do parametric simulation where one can have dimensions done in Autodesk Inventor, and these dimensions can be used to drive the electric or magnetic simulation. So that's parametric. Finally, with regards to licensing, we support activation-based licensing, which is the standard default license type. For an additional fee, we also support network license. Okay. Again, we are a CAD embedded EM simulation company. That's what Emworks is, and our products are all embedded inside CAD. Okay. We are embedded inside Autodesk Inventor, we are embedded inside SolidWorks, and we are embedded inside SpaceClip. However, the topic for today is more relevant towards Autodesk Inventor. If you need to understand how we work with other CAD, you're welcome to browse through our YouTube channel where we have other webinars which are dedicated to SolidWorks or SpaceClip. Now before I commence, there's a small promotion from our sales department which I do want to bring to your notice. This promotion expires December 31st, 2016. Here we get EMS magnetic for Inventor for we give for $10,000 US with 1 year maintenance, and that's a 33% off from the regular price. So if you're interested to know more about it, here are the contact details: sales@emworks.com, or feel free to call us at 514-612-0503. Now let's delve into the EMS applications. Okay, EMS can deal with wide varieties of applications from low frequency to high frequency. Now we are not going to bother about the high frequency for today's presentation, so the right hand side of this slide is something that I will not be covering. Okay, but we do have products that cover this, and should you have interest in them, please feel free to contact us. Now the supporting product that deals with low frequency, that is all the way from DC signal, which doesn't have any frequency, all the way to a few hundred megahertz. The EMS product can support those kind of frequencies. Okay. Now there are several different types, or I would say application areas in this EMS products. First of all, one can simulate electromechanical devices like solenoids, motors, generators, maglevs, magnetic levitation, speakers, magnetic recording device, all kinds of devices that work on the principle of magnets, magnetic field and magnetic energy. Okay. We also then support from the electromagnetic point of view. We have coils, permanent magnets, sensors, high voltage, high power devices, inductors, PCB, etc. We also support that type of application. From the power electronics, transformers, converters, bus bars are things that one can simulate using EMS. Also finally, EM behavior can be simulated. One can understand the amount of leakage. One can understand how effective is your electronic components shielded and so on. So that kind of EMI, EMC type of behavior can also be simulated using EMS. Now in the bottom you see some key industries. We deal with a wide range of industries, right from automotive, transportation, aerospace, consumer products, biomedical, energy, etc. So you can see that the application areas range from wide variety of industries. Now on the right side, I'm just going to briefly dwell about, we have our high frequency applications. That's a completely different product, but that deals with RF, passive RF and microwave components. If you want to simulate an antenna, for example, or a waveguide or a filter, RF or microwave frequency, you would be able to do that. We have suitable products and technology to be able to do that as well. Now let's get into the topic for today, which is the inductor. So as the name suggests, inductors, they are they are basically energy storage devices, and they store energy in the form of magnetic field. On the right side, I have three different classification of inductors, basically starting from what type of core they have. Majority of the inductors are just air core, which means this really just the wire as you see here. It's basically made of a conductor material like aluminum or copper, and there is no core present. So when you pass current through this inductor, then there's going to be a magnetic field, and it can store energy and so on. Okay. Then the next classification, or the next level of inductor, I would say a less level of sophistication in this inductor, is the ferrite core inductors, or you have some sort of a core which acts as a conduit for your magnetic field. Obviously ferrites have a much better magnetic property than air, and so hence this inductor has a capability to store a lot more magnetic energy or magnetic flux. So this is a ferrite core inductor, as you see here, is the next degree of sophistication. And finally you have a laminated core. So these are cores that are laminated, and laminations are introduced for certain specific reasons, especially to reduce the amount of eddy currents, to reduce the amount of losses due to the core, and so on. Okay. So you have several types of inductors depending on what kind of core they have. Okay. Application field is quite wide, but basically anything to do with energy storage, transformers, filters, sensors, inductors play a good role here. Now, as far as EMS is concerned, how do we excuse me, enable the simulation of inductors? EMS can, so first before I start, we can deal with all these three types of inductors that you see here. We can calculate the magnetic field distribution and the induced currents. We can compute the losses in the core, obviously losses in the windings as well. we can include the effects of laminations on the core, and nowadays you know, more and more sophisticated inductors for high applications obviously does include laminated core. For example, transformers, hardly today's transformers you would not find without laminated cores. So we can include the effects of lamination inside our our solvers, just to make it a lot more real life and a lot more accurate with respect to what's happening in real life. Okay. Obviously, customers are interested in calculating the inductance. You know, if you have one coil, it's just the self-inductance, but if you have a series of coils, then we're talking about self as well as mutual inductance. Induced voltages, flux linkages, these we would call as some kind of circuit parameters that helps you to characterize the your inductor design, so that you can use this in other upstream or downstream packages, something like a circuit simulator or things like that. So we can compute all circuit parameters relevant to an inductor. And finally, you know, one can also couple EM simulation to multiphysics thermal, where one can calculate the temperature distribution in the core due to the current, or I would say the eddy currents that are formed due to the AC signal or any kind of transient signal in the inductor. Now with this, let me quickly go over to a demonstration. What today I will be showing you the interface of EMS for Inventor. We're going to take a simple laminated C-core inductor, as you see here in the picture, and we're going to see how one can do the simulation of such a structure. What are the key objectives of the simulation for today? First of all, I will show you how to set up a simple electromagnetic simulation in EMS. How do you assign materials, how do you define coils, and so on. Next is the important topic of lamination, how lamination is incorporated as a material property, how do you define laminations. Then we will solve, and then we will determine how to study properties like the flux density distribution inside the core, how do you compute the solid losses, how do you turn on thermal and see how hot the core gets, and so on. And we will see how to create a simple engineering report, a simulation report, right inside the product. Okay. With this, let me just go ahead and turn on my my Inventor. Okay. And now this is the model of the C-core done using Autodesk Inventor. Okay. So I have a coil here, as you see. Then I have a C-core, and there is also air around this one, which I've hidden. So let me go ahead and just make it visible. Now, the importance of air is the magnetic field due to an inductor in this case of arrangement exists not just in the core, but also in the air region surrounding the core. Okay, and also in that little air gap that you see here. So it's important to model this air region. As you see here, it's modeled just as a solid inside a part inside Inventor, and one can assign a particular property to it like air, okay, which we will do that inside EMS for Inventor. Let me go ahead and hide back the air region. That's what I typically do, is get that out of the way. Let me go back to how EMS works. So let's go to the EMS feature manager now. The EMS feature manager is organized here, and you also see some icons that are more relevant towards electromagnetic simulation. The first step in creating EM simulation is to define what is known as a study. So you can define a study, and you can assign a specific study name to it. You can select what type of solver you want. We also support parameterization. As I told you before, if you have dimensions linked to your model in EMS, you can make use of that and do your simulation and see how the simulation results vary with the various geometrical dimensions, you know, a variation of these geometrical dimensions. As far as the analysis type concerned, as I said, the broader classification of magnetic and electric is captured here in the form of studies. Inductors basically run on AC signals, so you can have AC magnetic, but one can also have a signal that varies as a function of time, may not be sinusoidally, and for example some kind of a pulse variation and so on, and all of those can be tackled using what a transient magnetic simulation. Now you can specify the frequency. In this case it's the regular frequency of 50 or 60 Hertz, and you can ask the program to compute the circuit parameters. As I mentioned before, if you're interested in thermal, you can request the program to compute the temperature in the core as well. Now this is defining a study. Once you define a study, it creates what is known as a study tree, as you see here. Okay. Now the next step in defining the simulation is to create materials. As I mentioned before, the air geometry that is right around it, you can apply material, you can go to apply materials. Now EMS comes with its own material library. As you see here, this is a completely customizable material library, so you can choose from a family of materials that we provide, or you can create your own material and assign it and use it for simulation. So now this is air. Now it has a few properties, and you can apply air. Similarly, I applied copper to the coils here, and also some kind of a steel to the core that you see here. Okay, you see a little lightning symbol, and that's to compute the eddy effects. So basically, we tell the program to compute the eddy effects in components that we are interested in. In this case, we do want to understand the eddy effects on the coil, and that's what is creating some kind of a loss, a solid loss in the coil, and also will be responsible for any heating whatsoever in the coil. Okay, so EMS is capable of computing the eddy effects in the coil. Once materials are defined, the next step is to define a coil. Now this is the step where we define a coil. Now coils in EMS can be either current driven or voltage driven. In this case we can have a current driven coil. We specify the coil properties, basically the wire gauge of the copper wire that is used to create the windings, and then we specify the components that comprise this coil. Notice here that the coil is just modeled as a 3D solid model. It just represents the volume represented by the copper. So there are many strands of copper that go into creating this coil. You don't have to model these individual strands. You can just model them as a 3D solid model, as you see here. We can tell the program at what phase the current comes in. So basically it's this phase here, which is the cross section of the coil through which the current enters in. And then we specify the number of turns, we specify the current, RMS value of the current, and that pretty much completes the definition of a coil. Okay. In this case we have two coils. In this case we have just, just one coil, but EMS you're not limited to just having one coil. So if you have many coils, and in the case of transformer you're going to have primary and secondary coil, probably 6 sets of coils. You can actually define all of them and use them for simulation. Okay. Once you define a coil, we are all done and we are ready to go ahead and do the simulation. Now EMS is a finite element based program. What I mean by that is all the geometry elements, all the geometry is discretized into small finite elements. Now that's accomplished with what is known as a mesh. Now EMS has automatic mesh generation features here. So let me just go ahead and show you the mesh. Now it creates an automatic mesh based on your geometry. We also have powerful mesh control features that help you to define mesh controls in components, mesh control in faces, etc. Okay, let me go ahead and hide the mesh. Now once this is done, I had pre-solved this problem before this webinar. So let's go ahead and take a look at some of the results that that we can obtain from EMS. Okay. Now we will just refer back to some of the objectives. So let me just look back on the objectives. Okay. Now how do we set up, assign materials, define coils has been covered. Let's go to define laminations. Now in this particular C-core definition, I have, let me go ahead and edit the material. Now you can actually specify lamination. Usually in this case, if you see, it's in the global Z direction. So you can specify lamination, and you can specify what is known as a stacking factor, and that represents the volume of steel in the whole volume. So if you have insulator between these laminated steel sheets and that insulator occupies 8% of the volume, that's what the stacking factor of 0.92 means. So specifying lamination is extremely easy. So you can just select the material property, material for which you want to specify the lamination. You specify the direction of lamination and the stacking factor. So now we did the simulation. Now let's take a look at some of the results. So now most of the results, engineering results, are available in the form of result table. So when I click on the result table, I have access to a lot of results that you see here. So when you think about an inductor, we are really thinking about the inductance. So what is really the inductance of my winding here? Now the inductance of my winding is about 1.8 millihenry for this particular model. So EMS automatically gives you this result. In addition to the inductance, you can look at the flux linkage, here the real and the imaginary part. You can look at impedance, you can look at the solid loss as well. So here you can see the solid loss of the core, that's about 0.032 watts. Are really not much, and that's really the effect of laminations, is to reduce this solid loss. So you can also compute the winding losses which are available for you. So all the engineering results are actually stored in this result table, and this is one of the most important places that our users go to once the simulation is done. Now, as I mentioned earlier, this is a 3D field simulation software, so all our results are available as 3D plots as well. So now let's take a look at the magnetic flux density as a 3D plot. So we can double click, and now you can see the distribution of magnetic flux density as a 3D plot. So I can actually move this over to look at it here. So now this is the magnetic flux density, and this is you can see the values here as a 3D plot. Okay. Now one can actually take a section view of it. So I'm going to go ahead and take a section plot, and which helps you to actually see the distribution of your magnetic flux in the core right inside the core as well. So that's available to you as in the form of a section plot. Okay. So magnetic flux density you can visualize. You can also visualize the field intensity, the current density, and so on. So for example, we're going to have some eddy currents in the core due to this AC excitation. So one can actually take a look at the magnetic, the current density in my core. So you can actually take a look at this one. So you can see the current density obviously in the coil is much higher because there is applied current, but there is also current in the core. So you can take a section view of it, and you can see the current density value in the core, which is actually much less when compared to the one in the coil. Okay. Now one can also study the loss density. So this is a section plot of my loss density. Okay. So you can see that the induced current is the one that is responsible for the losses, and you can see where the losses are high, which is proximity closer to the coil is where you have slightly higher losses, which is brought about by the green and yellow and the red color, and away from there the losses are quite low. Okay. So EMS can visually give you insights into your model. Electromagnetic fields are quite complicated because they really, you can see them using your naked eye. So, and also it's really difficult to have probes inside your model, especially the core, to understand what's going on. So it's quite nice to have a 3D field simulation to really zoom in and understand what goes on inside your model. Finally, I'm going to go ahead and take a look at another nice feature inside the product, which is the automatic simulation report generator. So every simulation comes up with an automatic word report, okay, and this word report, as you see here, is again, this is the word report that is created right inside EMS for Inventor. So it has a description of the model, and believe me, this is completely customizable. So you can type in things that you want to and share it. So it contains the information about the coil, It contains information about the windings. All the results that you saw in the result table is there. You also have the plots that we saw. So all of them are nicely come out as a word report. So here is a vector plot. Here is a plot of losses. One can plot the quantities as vectors, as well as plot them as just colors here, as you see here. So all of this is neatly captured in a fully customizable Word format automatically for you. Okay. Now let's go ahead and take another variation of the same study. Now this is a study with thermal. So what's the difference between the first study and the second study is, let me go to the properties, and here I have made sure that I want to understand how hot my core gets. So I've turned on my steady state thermal simulation. Now I specify convection, so we want to understand what's the boundary condition. What really happens between the solids that you see here and the air. So what happens is a simple convection process. Now this is air-cooled inductor. You can have oil-cooled inductors and so on. So you can actually vary the convection coefficient of the convection that happens from the solid to the air. So right now we can passively cooled just natural convection with the convection coefficient and the ambient temperature. So if you define that, you can actually study what's the temperature in the core. So here we did that, and we can compute the temperature in the core. Now this is a plot of the temperature in the core, and you can see how the regions which are closer enclosed inside the coil gets much hotter than the regions that are in the outer. So now you can not only have the ability to look at the flux and the current density, etc. One can also couple this with steady state thermal simulation to understand what's the temperature distribution inside the core. Okay. With this, pretty much this completes the demonstration part of my of this webinar. So I would just want to go back to my slides and use this slide as a recap. So what we just saw here is how you can set up a simulation inside EMS. They are organized based on what is called as studies. It's extremely easy to use. Once you create your model in Autodesk Inventor, you can make it almost ready for simulation at the same time. So you can create a study, assign materials, and define a coil. You can define laminations if you have them. You can then solve using an automatic mesh generation process inside the program, and then you can take a look at 3D results in the form of magnetic flux density, the field intensity, etc., both as 3D plots, as vector plots, and so on. You can also compute the solid losses, and finally you can study the temperature distribution in the core by coupling it to a steady state thermal simulation. Okay. And finally, one can create simulation reports with a click of a button. It's done automatically for you. Okay. Now EMS is used worldwide by over 450 customers, so we are certainly trusted by some of the big names in the industry, and also all across across different continents in the world. Okay. And you can see here that it's a testimonial for our success as a product. And some of our customers use this to create wonderful products. Okay. Now, finally, I would like to thank you all for taking the time to attend today's webcast. Please visit the Autodesk App Store. Actually, the full version of EMS is available for a full 15-day trial at the Autodesk App Store. So you're welcome to visit that, and you can download the product and please try for yourself. There are tutorials, learning resources, etc. that will help you understand how this is done. Okay. Finally, if you do have a problem that is related to electromagnetics, we are always there to help you understand and see if our solution fits your need. So you can contact our technical team and ask to speak with a technical person, and we would be glad to understand your problem and see if EMS is a solution for you. you can contact Adam at this number, or send an email. We'll be always happy to connect with you. Finally, you can visit our website, emworks.com. You can view our white papers, see what customers like you do, and see how EMS product can benefit you. Okay. Before I sign off, I would like to again reiterate on the promotional offer which expires end of this year, and you get a 33% off on the regular price for EMS magnetic, and everything that I showed you here is covered in the EMS magnetic product. You can contact, the contact information is there. Okay. With this, we would like to open the floor for any questions if there are. Okay, there are a couple of questions which I would quickly answer. Is EMS capable of doing non-sinusoidal excitations or currents? Yes, today we saw EMS, we saw sinusoidal current where we applied RMS value of the current, but if you do a transient magnetic type of simulation, you can have any profile of current or voltage versus time. So it can be sinusoidal, it can ramp up quickly, it can be exponential, it can be like a step type excitation and so on. So we are not just limited to sinusoidal current, so you can have any type of excitation. Is EMS capable of studying the eddy currents in the core? Yes, certainly, as we showed you in the demonstration today, you can compute eddy currents for components of interest to you. Basically in these type, it's mainly the core. And you have to turn it on. It's a feature inside the software. You have to turn and request the software to compute eddy currents on specific parts, and you also have to make sure that those parts have conductivity as a property in them. So as long as you have conductivity, you can do eddy currents type of simulation. Okay. And there's also a question which says, can EMS solve solenoids and those type of applications? Absolutely, it's a program that is that can do any kind of magnetic type of problems. So if you have solenoids, actuators, etc., EMS will be able to compute the forces due to magnetic field on your ferromagnetic components that move, and you will be able to do that inside EMS for Inventor. Okay, how exhaustive is the material library in EMS? The material library in EMS comes with the pre-packaged materials. They cover conductors, ferromagnetic substances, biological materials, insulators, ceramics, and so on. So pretty much most of them, and of course ferromagnetic steels with its own BH curves. We do cover most materials that are commonly used. Having said that, we can cover every material that's out there. But the nice thing about our material library is it's completely customizable, so one can actually create your own materials with its own curves and so on and use that for simulation. Okay. And last, I would like to tell you about some of the learning resources that we have for the EMS product. So we have a full suite of tutorials and help, and also a lot of YouTube videos that will help you to learn EMS products. So we have learning resources that will help you get started with the product very quickly. Okay. With that, pretty much we come to an end of this webinar. On behalf of Emworks, I would like to thank you all for patiently listening to this webinar. I hope it was enjoyable and also informative. And if you have any questions in the future, these are our coordinates. Please feel free to contact us, and we'll be very happy to help you with your problem and see how EMS can find out a solution for you. Okay. With this, have a nice day, rest of your day. And we'll see you in a future webinar, or look forward to talking to you about understanding your application pretty soon. Well, thank you very much and have a nice day.